Today we'll be discussing Lab 4, Magnetic Braking with Faraday. So the purpose of this lab is to observe the interactions between a falling magnet through a conducting aluminum foil tube using Faraday's law, and use a computational model to compare with our experimental data. And just a quick preview of the results. For the experimental data, it was averaged out at about half a second for the magnet to fall through the tube, and the computational model said that it would fall through the tube in about half that time. And so the concepts that we'll be using will be Faraday's and Lenz's laws, the Biot-Savart law, and Newton's second and third laws. And you can find them on this slide here. And so for this experiment, we'll be dropping a magnet down a foil tube 5 times and finding the average time it takes for the magnet to travel through the tube. The system is the magnet, while the surroundings are the foil tube and the earth, and listed are the initial conditions. So after experimentation, the average time it took for the magnet to travel through the tube came out to be 0.504 seconds. And here are the results of the computational model. And right now I will highlight all the changes that I made to my GlowScript code. And I will also leave a link in the description. So discussing results, the red current is counterclockwise, while the blue current is clockwise, since they work together to slow down the magnet's descent. And when the magnet is flipped, both the magnetic field and the induced current are flipped, but everything else stays the same. The results in the computational model are a lot lesser than the experimental results. And as seen with the graph, gravity has an initial influence, but the magnetic force is present to slow the magnet down. And there may be a couple reasons why that computational model is a lot lesser than the experimental results, being negligence of air resistance in the computational model, maybe some human error with measuring times at which the magnet entered and exited the tube, and also the magnet coming into contact with the tube, which would slow its descent even more. So what if the resistivity of the conductor were reduced as close as possible to 0, and how would the dynamics of the falling magnet change? So as the resistivity approaches 0, the current increases to sustain voltage. A larger current will result in a larger magnetic force that still points anti-parallel to the force of gravity, thus resulting in the magnet falling much slower. And what if holes or slots were cut into the tube? How would this affect the ring currents in the model? The holes and slots would disrupt the induced current and in turn decrease it, and the decreased induced current would reduce that magnetic force, and as a result, increase the speed at which the magnet falls. And that's it. Thanks for watching, and have a nice day.